So when I post it, I can post this as chapter 12. It's those small things that I have to remember, right? Okay, so we're working on chapter 12. In this section here, we're focusing on the behavior of solids. I have taken a lot of the content out because I looked at the learning objectives to see what you're required to know, and I was trying to focus just on that, okay? We are focusing on crystalline solids and their structure. So we're told there's a lot of solids out there. There are amorphous solids, solids like pencil lead, where the atoms are not organized in a very orderly fashion. We're going to be focusing on crystalline solids like the solids you see in sodium chloride table salt. These crystalline solids, first, when they form a solid, to our eyes, structure looks like a crystal, kind of like table salt crystals, right? The atoms in there are orderly. They're arranged in a very orderly fashion. They are orderly geometric structures whose lattice points are occupied by either atoms, ions, or molecules. Ions, atoms, or molecules are organized in a very, very organized fashion where they have some kind of geometric relationship. Okay, something like this picture right here. For that reason, when we're looking at these, we're going to be thinking about some kind of geometric relationship. So we're told here the study of solid structures is often done using X-ray diffraction. When I was in school, this was one of those sections where I was like, oh, this section is so boring. I really think, not to throw my teachers under the bus, I think the section itself is so-so. I have one student who went into material science and he loves this. So he's an interesting person. So when he talks about this, he makes it interesting. My teachers didn't really do that. So I didn't really like this section. But this part of the section I really liked. I mean, I was good at it, I just didn't really like it that much. I didn't really enjoy it that much. Our focus here will be to look at how the atoms relate to each other and how the atoms pack. Because at some point we see on a practical level, the way these solid atoms pack determine the physical properties. We did say in the last chapter, intermolecular physical properties. Now we're saying the way the solid atoms in a solid pack determine physical properties. What are we seeing here? Here we'll be looking at things like density, and that relates to durability, maybe even weight. Okay? For those of you who want to go into engineering, this is important, right? If you're asked metal to perform a certain task, you want to know what the role of that metal is. Do you want the metal to last a very long time? You want to select a metal that has certain physical properties. Okay? So going back to this, we're told, allowed to cool slowly, the particles in a liquid will arrange themselves, they will align themselves to give a maximum attractive forces. So we're starting by going from liquid to a solid. Okay? In looking at the solid, how is that crystalline lattice made? It's made when these atoms are allowed to cool naturally, organically form those intermolecular forces. And remember, solids tend to have relatively the highest intermolecular force compared to, of course, liquids. Okay? When the molecules are attracting each other a lot, they minimize energy. From 1411, one of the personal goals or the atomic goals of the elements is to minimize energy. In this case here, they accomplish that by forming those strong intermolecular force. And when they do that, they form a crystalline solid. So let's go back to table salt, okay? Table salt is one of those examples of crystalline solids. Table salt, sodium chloride. Has any of you tried to melt table salt? I don't know why you would do that, but I just want a yes or no. Have you tried to do that? I have never personally tried to do that. Okay. I've never personally tried to melt it because even when you're cooking, you never really start with a table salt. So I've never tried to do that. But I have cooked foods where I've had to melt sugar, right? As part of the process, you're caramelizing and stuff. It takes a lot to melt salt. Part of that is, of course, those high intermolecular forces, right, in table salt. So we're going to be seeing that the arrangement of the particles in the crystalline solid is called the crystalline lattice. Since we're looking at a setup where you have a lot of atoms or molecules arranged in the solid, we will pick just one small portion. So this picture here shows you what we're doing. Imagine this was your solid. By the way, remember from before, solid particles are actually arranged very close to each other, like that, okay? But for us to see what's going on, they have spread them out for us to easily see and understand what's going on. But in reality, they're packed very close together. Okay, what we're going to be doing is we're taking one small segment, one small portion of the solid and studying that. When we are done, we are extrapolating or we are applying what we learned to the rest of the solid. So it would be like learning this small part here and applying it to the rest of it. That just makes the learning process a lot easier. So that small portion in the solid that's isolated to be studied is called the unit cell. Okay, this is the smallest unit that shows the pattern of arrangement for all the particles in the cell or in the matrix, right? So you have all these atoms arranged. You find a small part and then study that and apply to the rest of it. But the small part you find is very unique. It shows the pattern for all the particles, okay? So I like to relate chemistry, of course, to life outside chemistry. I don't want to call it real life because chemistry is real, right? If you've ever had to decorate a bathroom or pick a tile or something, or if you just like looking, right? I like looking at tiles, okay? If you like looking at tiles that have patterns, or if you just notice that, usually there is a whole mosaic, the whole design, right? There's a whole design of the actual tiles. The individual tiles that the designer designs is such that if you stack the tiles side by side, top and bottom, and then you install them and you step back, you see the whole design. So the way we have the individual tiles stacking together to give you the whole design is the way we have the unit cell here stacked together to give you the whole arrangement of all the of all the molecules, right? So the unit cell here is similar to single tile. The difference though is that the tile tends to be more 2D and the unit cell is actually 3D. The unit cell is more like a block. The single tile is more like it's more flat, right? So you install it with grout and all that stuff. But when you put everything together, you step back, you see the design, everything looks good. Unit cell is more 3D. Okay, so we're told here the unit cells are three-dimensional and they're usually containing 2 or 3 layers of particles. So sometimes it's just one layer, sometimes it's 2 or 3 layers of particles. Okay. Remember, for the unit cell, if you repeat this over and over and over, so you take a bunch of unit cells, kind of like Legos or tiles, and you stack them over and over and over together, you get the macroscopic crystalline structure. So take one unit cell, stack it with another, and another, and another, and another, and then step back and look, and in the end, you get the full picture showing you all the atoms and how they're related to each other. Okay. And that full picture is the macroscopic level, the level you can see with your eye. So here's an example of a unit cell. You can see it's a cube, right? And it shows you at least 2 layers of atoms. So we'll study that in a second. It says here, starting anywhere within the crystal results in the same unit cell. So your goal is to find a pattern or an arrangement of atoms, right? That you can kind of take out, where if you stack these over and over again, you get the whole macroscopic view. We're told here each particle in the unit cell is called a lattice point. So at this point here, these words, you want to just be familiar with them. I'll start with a simple cubic. With simple cubic here, you can see that it's hard to see the different. I'll try to map it out based on what I'm seeing here. But we have a cubic cell, right? So this is a cube. That means from here to here, what do you call this? The width, the height, and the length. These are all the same distance or the same dimension, the same length, right? So you have all these the same length. At the corner of this cube, you have atoms. We don't have the full atoms in simple cubic. We actually have 1/8 of the atoms in simple cubic. It's hard to see this here, but I'll try to map it out so you can see. This is how it looks. We have an eighth, or yeah, an eighth of the whole atom right here. Same thing in this other corner here. You have an eighth. So I'm going to be telling you the fractions of the atom, of the whole atom that exists in the different arrangements of the cell. Okay, so we got that there. So when you look at this, we have 1, 2, 3, 4. Okay, so we have 4/8 pieces on top. And on the bottom, we have another 4, right? There's one here. I guess I should call this 5. And then this one here, another piece, the 6th piece. This would be the 7th piece right here. Hopefully you can see that. Then this would be the 8th piece. Do you know one summer when I was teaching this on campus, I actually bought some oranges and spent the time cutting all of this together while the students were working on the worksheet to show it to them. I mean, it was a lot of work. I used oranges and toothpicks. When I got done, I showed it to them. They looked at me and they said, "Ah, okay, I guess." I'm like, "Are you kidding me?" I spent so many hours. There was a lot of oranges. The whole place smelled like oranges. Anyway, yeah, I'm very visual. So actually working on the activity helped me to really see it, right? You cut the orange in half, cut it in half again until you get it 8 pieces, and you arrange them using toothpicks. And they were like, "Yeah, sure." This arrangement here is called simple cubic. In simple cubic, you have 8 of the 1/8 pieces in the unit cell. Okay, so you want to know when you're given a unit cell, you want to be able to recognize, is this unit cell simple cubic? Does anybody have any questions? So simple cubic will always have 8 of the 1/8 pieces of a whole atom in the unit cell. Okay, and remember, these are called corners. So the 1/8 pieces are in the corners of the unit cell. Okay. As we're looking at the unit cell and trying to figure out the behavior or the characteristics or the properties of the metal, we're going to be looking at something called coordination number. The number of other particles that each particle is in contact with is called coordination number. Now, I like to relate this to the number of surrounding groups. Remember in 1411, we had a central atom, I'll call it a general one, surrounded by so many surrounding groups, right? In this context here, we will have a central atom that you select, right? And you're trying to see how many other atoms are in direct contact with your central atom of interest. The number of atoms based on this picture I have here is 4. Okay, so the way I've drawn this picture, you can conclude the 4 atoms are in direct contact with A. So that means A is the central group I was focusing on. For that reason, A has a coordination number of 4. Okay. Does anybody have any questions? Okay. If not, I'll ask the question. What if I had more groups in here, like I had others, like other atoms? How will I know which ones are actually in contact with A and which ones are not? Because I don't have a model in front of me, right? I don't have a model I can touch and I can turn around and twist and, view from different angles to tell what is what. I just have a 2D picture trying to describe a 3D situation. Okay, so I asked a question and I'm going to answer it. Most of the time, Understanding those challenges, the authors will kind of draw a dotted line to assist you a little bit to see what is in context. So then you can tell the ones that have the dotted lines are in context, the other two are not. Or they will describe it in words. Does that make sense? Yeah, they'll try to help you recognizing this is not very easy. Okay. We're told here for ions is the number of oppositely charged ions with which the ion is in contact with. So we're going to be doing some practice problems so we can see how this plays out. So we're told, I guess you're asking the question, why am I learning coordination numbers? The higher the coordination number, it means the more interaction, therefore stronger attractive forces hold the crystal. If you have stronger attractive forces, this is back to chapter 11, right? If you have greater coordination number, I'll write this shortly, that implies stronger or higher intermolecular forces. That means more dense and probably higher melting point. Okay? So when I think about application, when I think about the relevance of this, I think about cars. So when I was in college, my friend got the Prius. Okay, now my husband and I we have the Prius. I think about cars. And when he got the Prius, he's like, "You want to drive my car?" I'm like, "Sure." I had just learned how to drive. I was all excited. Let me drive your car. And I went to school in Commerce, so I'm going off of Highway 50 to Highway 30. And I'm taking that curve onto the highway, and then the wind blows. And I was so afraid because I thought it was gonna blow that car off the highway. If you've ever driven a Prius, you understand what I'm saying. I'm not saying they're bad because currently my husband and I own a Prius. Okay, socially responsible. Anyway, I felt the wind in that car, not in a good way. I could actually feel it, and I had to kind of overcorrect, not over, but correct just right to stay on the road. And I was like, this car is dangerous. Well, what did they do there? They used a lower density metal to decrease the. I'm oversimplifying this, right? But they used a lower density metal to decrease the need for high to decrease the load on the car so you can get a high miles per gallon. So the trade-off is the metal is lower density, the car has high miles per gallon, and you can go really far in that car with a full tank. But that was the trade-off. So when the wind was blowing, that car was so light. And then yeah, so then I got an SUV. I'm like, this is more like it. The SUV, man, you can't get far with gas, but the metal is more dense. You can tell the difference when the wind blows. I'm like, what wind, right? Very different. So different metals have different properties because it boils down to the coordination number. How many of those atoms do you have in a specific amount of space? Higher coordination number, greater intermolecular force, and then more dense or less dense, right? Okay, and so there's something called packing efficiency. And the packing efficiency also communicates how well those atoms have packed. It's like we're judging the atoms. If they're packed very well, of course, if the packing efficiency is very high, you have a more dense metal and you have a more durable metal. Okay, once again, for the designer, the engineer, the type of metal picked has to line up with the purpose or the function of that metal, right? You want to make sure you pick it right. Okay. So the higher the coordination number, the more efficiently the particles are packed together. We talked about cubic unit cells, right? So now we're going to be talking about the fractions of the whole atom in different parts of the unit cell. So we're told here, I want you guys to write this, right? If you have a unit cell, this is just generic, not necessarily this unit cell. If you have an atom, now these right here are representing the atoms. If you have an atom in the corner of the unit cell, then it's usually 1/8 of the atom. So as you guys write this down, I'm going to write it down too, just so I can visually see it. So the corner pieces of the unit cell, I guess I can write this out. Okay, let me add a page here to write it out. So we want to know the fractions, right? So in a unit cell, this is just general, you have different pieces of the atom. Number one is going to be the corner pieces. the corner pieces are 1/8 of an atom. So when you see the corner pieces, you can conclude it's 1/8 of the whole atom. Okay? The corner is right here. So I'm going to say this is a corner, this is a corner, this is a corner, this is a corner. And we usually have 8 corners, right? There's a corner back there, a corner up here. Okay. Number 2, we have something called the face piece. The face is right here. So I usually try to imagine, okay, that I am in the room that's the cubic, the unit cell, like I am inside that room, okay, inside the cubic, the unit cell, the cubic shaped unit cell, and I imagine the corner of that room essentially having 1/8 of the atom. And then when you look at one wall, the wall is essentially what is called the face. So the face, aka the wall, all that unit cell usually has 1/2 of an atom. Now I'm saying atom, they're saying the word particle here because it could be an atom, it could be an ion. Okay. So we have 1/8 that goes with corner pieces. The face or the wall is 1/2 of the atom. Okay. And then number 3, we have the edge. The edge of the cell has 1/4 of the atom. So the edge will be from one corner to one corner. That distance between the one corner to the one corner, that will have 1/4 of the atom. Okay. So if you're wondering where they're getting these numbers from versus just memorizing it, you can be a great memorizer and all this information is fine. For me, I'm sitting here, when the kind of learner I am is the suspicious one. Okay, I see these numbers and I'm following along, but where did you get these numbers from? Why 1/8? Why 1/2? Why 1/4? What if I forget? Because I have that kind of wandering mind, right? What if I forget? So let me do the last one and then I'll talk to you about how they get these numbers. The last one that's not in the list here is if the atom is in the center. So in the center of cell, we have the one atom. They don't bring this up, but we find scenarios where that's the case, one center. Okay, so how do you get these numbers here? Okay, if you're forgetful like me, which I am, very forgetful, and I own up to it, it's just part of my constitution. They take 4 of the unit cells 4 of the unit cells. This is my horrible picture, y'all. I'm stuck. Okay, let me zoom down because they have a better picture here on the bottom somewhere. Yeah, like that. I was trying to draw this and I was like, why am I even trying to do this to myself? I know I can't draw. I can't. Okay, they take 4 of these unit cells, right? 4 on top and then 4 on bottom to make 8. So they take 8 total by stacking 4 on top of 4. And you can see that here. And sometimes, for the most part, it takes 8 unit cells to kind of begin to see atoms as wholes and not like whole atoms, not as pieces. You see how in this picture here, when they took 8 unit cells and stacked them up, 4 on top, 4 on the bottom, now we're not just seeing the pieces of the atoms, but we're seeing them as whole atoms. And if you keep adding, of course, on top, on the side, on the bottom, and either, you will see the atoms as whole. Okay. So as we were looking at the simple cubic cell, if you look at just one, you see the atoms as pieces. But if you take 8 together, they look more. For the ones that are on the wall or the face, you essentially see one atom dividing two. So one atom right here divided between 2 unit cells. So let me put it to you like this. The bottom number that I was talking about here, this bottom number shows you the number of unit cells that the atom is divided between. So this one here, this one atom was shared between 8 unit cells. So each unit cell got 1/8. This one here was shared, one atom shared between 2 unit cells. So each one got 1/2, right? This one here, based on its position, is shared between 4 unit cells. So each one got 1/4. This one here is not being shared because it's in the center of one of the unit cells. So the 1 unit cell gets the whole atom. Okay? So that's the simplest way I can explain it. The number of unit cells that the atom is equally split between determines the fraction that we see. Okay? Now let's go into it. Now that you have this fraction, we'll use this to work out the problems in this PowerPoint slide and therefore your lab. Okay. In the simple cubic unit cell, we saw that we have 8 particles, but not 8 whole particles, 1 at each corner of the cube. And remember I told you the fraction of the whole particle we have is 1/8 of each particle. So one of the things you have to do here is calculate the number of whole atoms. I say atoms, but I mean particles, right? It could be atoms, ions, whatever. Whole atoms, particles. Okay? So we're going to be looking at 3 things mainly in this section here. Number of whole atoms or particles, and then they can ask you to find coordination number. And at some point, we'll be doing empirical formulas. Remember that from before? Yeah, we're doing that here. Okay? So if we have 8 corners and each corner has 8 pieces, back to the picture that we had over here, right? I have 8 corners. Each corner has a piece that's worth 1/8. I can say if I took all those pieces together and combined them to make a whole atom, I'll only get 1 atom out of that. So we have pretty much completed objective 1, which is taking a unit cell and figuring out how many atoms we have in that unit cell. And you see that in your lab work, right? Find the number of atoms in the unit cell. Okay, next. Coordination number. For the coordination number, I was telling you that you want to identify your central atom and then figure out how many atoms are surrounding it. If I look at this unit cell as I have it right here, I can't tell what's in the center. There's no actual atom in the center. There's nothing in the center. All I have is corner pieces. So this is where it's important for you to have the 8 cubic cells because that gives you a bigger picture. You have a greater area. You can see what's in the middle. So I'm going to scroll down. I know I'm going back and forth, but I'm trying to get the information right here. So essentially, I took this here where I was able to get that I had 1 atom per unit cell. This is telling you if you kind of zoom out a little bit, you see how the 4 atoms are here like that, 4 on top, 4 on the bottom. And you see what sections of the atoms are inside the unit cell. All we care about is what's inside the unit cell. But when it comes to coordination number, we need a central atom. So here they're telling you to see the coordination number, which is 6. We'll see how it works out. Stack 8 unit cells together. So 4 on top, 4 on bottom. Once you do that, you're able to see. You see, I told you they're using the dotted lines to guide your eyes. So here, this then becomes your central one, right? And they use the dotted lines to kind of help you see. That means above this, you have this atom here. To the front of it, I'll say to the front, based on where I'm standing, you have this atom here. To the back, you have that atom. To the left, you have that atom. To the bottom, you have that atom. To the right, you have this atom. So this central atom here is surrounded by 1, 2, 3, 4, 5, 6 other atoms. Therefore, coordination number is 6. We're going to be learning 3 different types of arrangements, and in the end, we'll judge what is more efficient. Okay? So this is the first one. Let's see. Let me make sure I have done. Oh, I already went through all this, so we're good, right? Number of atoms. Yeah, I can skip over that part and go over this. Now, the next type of arrangement we're looking at, or the next unit cell we're looking at, is called body-centered. As a student, I'm like, oh, I heart chemists. I heart chemists. I love that when chemists are naming things, sometimes they're very literal. Love that. Guess what is in the center of this unit cell? A whole body, because it says so right here. Body in the center. Body centered. Okay. So it says here 9 particles. Where's the picture? Where is the picture? Oh, there it is. So, oh, I wish they put this picture up here. Anyway, they chose to put it down here. This is called body centered. Now, the center one may not necessarily be gold. They picked a different color so you can see it, right? If it was purple, it'd be hard to see one from the other. But you can see right here, I have the body center because there's a whole atom in the center. So that counts for one atom, right? And then you have 8 of these corner pieces. 1, 2, 3, 4, 5, 6, 7. And there's one in the back. 8. So if they ask you how many total atoms do you have here, the purple ones all together is 8 times 1/8 to make 1 atom. Then we have 1 gold one in the middle, 1 atom. Add these 2, and we have 2 whole atoms. They're always asking you about whole atoms because remember what Dalton said? Atoms do not chemically combine in fractions. It's whole. It's all or nothing, right? So even as they are arranged, we look at them as wholes, not fractions. Do y'all have any questions? Okay, so since you don't have a question, I'm going to ask the question. Will we ever have a scenario where we look at a unit cell and we see a fraction? I have never encountered a fraction. So I doubt that at this level you guys will. Okay. Okay, so in the body center, they're saying a lot of stuff here. As you guys saw, we had 8 corner pieces times 1, 8. And then we had 1 in the center. Okay, so they are saying coordination number is 8. Okay, since the answer is already given to us, we're trying to see if we can see this. Once again, from this step here, we have a little bit kind of like unit cell plus. They gave us the upgraded view of it where we have the corner pieces are now kind of made whole so you can see the whole atom, but not all of it is inside the unit cell. Only 1/8 of the whole atom is inside the unit cell because these corner pieces are shared by 8 unit cells. That's why each one gets an 1/8, right? Then you take the 8 unit cells and you stack them up together, 4 on top, 4 on the bottom. Okay, once again, you see the central one they picked is the purple color right here, purple color right here. So they use the little dotted lines to help your eye see. The purple color is kind of sandwiched between 4 gold on top, right? Without this, it'd be hard for me to see, and 4 gold on the bottom. So 4 on top, 4 on the bottom, that makes 8, okay? So we have 8 coordination number. So now I want to ask you this question. Of the 2 we've seen so far, the simple cubic, oh, come on, cubic versus the body center cubic. Which one do you think is packed more efficiently? What do you all say?
The body?
The body, right? Because it has twice the number of atoms packed inside the unit cell. Okay. Just when we think it can't get any better, then we go to the next level. Face-centered cubic. What do you think the face-centered cubic means? I mean, we literally have the picture underneath, but what do you think that's describing?
The face.
Really? You just left it as the face and you're like, yeah, she can fill in the blanks. Okay, right. Once again, it's just telling you what's in the center, right? Now, the face isn't necessarily located in the center. I feel like the face is facing the center, okay? Because when you look at this here, they're describing this situation right here. Wow, this is as far as I can zoom. No, I can zoom in further. The face, remember the face is the same thing as the wall. So you essentially have this huge atom, if you were able to get inside the unit cell, you have a huge atom coming from the wall, and you only see half of it. If you were standing somewhere in here in the middle, there, you only see half of it come from each wall, but the one half of the atom that you're seeing is coming all the way to close to the center of the wall. So you have a half of the atom from the right side, left side, front side, back side, top side, bottom side, right? So it's the face facing the center. That's how I see it. Okay. So now we have to do the math as usual. What's the value of the corner pieces, the purple ones? I like to go for those first because it builds confidence. Okay, corner pieces are worth what?
1/8.
1/8. And remember, in each cube we have 8 corners, so it's times 8, so we get one atom. Okay. Wow, we haven't done this one, so we kind of have to think about it. Okay, we've seen the value of each piece, right? Or the fraction of each piece inside the unit cell. How many face pieces do we have? What do y'all think? Based on what you can see over here.
6.
Yeah. Because think about it, you're in a room that has, well, ignoring the door, right? You're in a room that has essentially 6 walls, right? 1, 2, 3, and then there's a 4 on the other end. I can't draw it. It's 4 right here. And then top and bottom, 5, 6, right? So you're in a room that has 6 walls, 6 faces. So times 6, and each piece on the face is worth what?
1
What
6.
fraction?
1 6.
Mm-mm. You can see it in the picture right here, right? This is one half of the whole atom. So the wall pieces are being shared just between 2 unit cells. So you can see here in the picture, it's one half. This is like one half of the atom. The other half is in the the neighboring unit cell. So the wall pieces are one half. I'm trying to describe it, but all I can think about is a weird sci-fi thing where it's like what the brown atom was trying to, it looks, I mean, it's in the wall between 2 different rooms. So half of it, if you look at it from the side, half of it is in one room, the other half is in the other room. So if you want to see the whole thing, you have to look at it from outside versus inside. If you're in one room, you're only seeing half of it. So it's half. Okay. And there's 6 halves. So when you multiply these two, what do you get? How many whole atoms? 3 whole atoms. So when you add these, you get a total of 4 whole atoms inside this unit cell, face-centered unit cell. Okay? Now, for the coordination number of this, first of all, they don't use dotted lines, so they kind of leave me lost. I'm just going to tell you right now, it's hard for me to see this, but let me draw this for you. You have that, that. 1, 2, 3, 4, 5, 6. So when you count all of these, they say there's a coordination number of 12. Can I see it myself? No. Do I just believe what they say? Yeah, because I really cannot. It's hard for me to see how these 12 probably arranged to get all that stuff, but I just go by what they're saying. And I have never done this in the lab because I didn't really care much for this as far as research was concerned. It wasn't like it just didn't sound very exciting to me. Now, do I like diamonds? Yes. Do the arrangement of the diamonds atoms make a difference in how the diamond behaves? Yeah, I like the application of it. Just the research wasn't that exciting. Okay, but just recognize that when it comes to face center cube, this tends to be the most efficient packing. Okay, in one unit cell, you manage to get 4 whole atoms. Are these arrangements the only arrangement we ever have? No, we'll see other ones, even the examples. Okay, so 12 coordination number of the 3, this is the most efficient. So we have a summary here telling you how many atoms we have in the unit cell, what the basic arrangements are, coordination numbers. This is the part that we didn't do. We didn't go over figuring out the edge length or the packing efficiency. But you can see the one with the 4 atoms definitely packs a lot better, right? So if a metal has this property here, it will be the most dense and durable. Okay. Okay, so we get to practice here. Now we're taking what we learned and applying it to the last section of this chapter, which is determining empirical formula. Yeah, you heard it. Empirical formula. So we apply this to ions, right? Remember I kept saying atoms, atoms, atoms. They said particles, 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 because particle is a generic term that means atom or molecule or ion. It's just whatever particle you're talking about. So we use our knowledge to apply this to figure out the empirical formula. In 1411, for the empirical formula, we did that whole percent element, get to number of moles, mole to mole ratio. You remember all that stuff? Multiplied by that special number, da da da. We're not doing that here. What we're doing is we're using the number of atoms. So the number of atoms in unit cell essentially gives you empirical formula. Okay, that's the bottom line. So what I want to do here is I have done a lot of talking. I can tell because my voice is already like, yeah. So I want you guys to tell me, looking at this picture, we'll start with chloride because this is a corner piece. How many chloride atoms or particles do we have inside the unit cell? Because all we care about is what's inside the unit cell. How many do we have and what fraction?
1/8.
Okay, we have a fraction of 1/8. And how many pieces do we have?
8.
8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. We have 8 pieces inside the unit cell. We have 1/8. So we end up with 1 chloride ion. Okay, what about cesium? How many cesium ions do we have? Cs plus. What do y'all think? Where is the cesium located in the unit cell?
The center, so it should be 1, correct?
Right, right. It's in the center, so it's just 1. So Cs plus, 1 Cs plus. Okay, now here's the thing. I said empirical formula, but I should have mentioned this is ionic compound. Okay, it's hard to find the empirical formula of molecular compound using this process because molecular compounds usually are more complex than this. But we use this to find empirical formula of ionic compounds. Okay, remember in ionic compounds, 1411, we write the positive ion first, the negative ion second. So positive first, negative second, or metal first, non-metal second, most of the time. Okay, so cesium is the metal, we'll write that first, and then chloride we'll write second. Okay, so I'm not going to do crisscross charge because that's not the method. The method we're using here is how many chloride ions versus how many cesium ions. We have one of each, so I write 1, and that's it. The empirical formula right there. Okay, so 1 and 1, 1 of each, right? 1 and 1. Okay. Now we're working on rock salt or table salt, sodium chloride, rock or table. Okay, let's see. Where's the picture? Oh, picture right here. They're describing it here. I'm like, where's the picture, people? They changed the slides a little bit, the one I was used to. Ha, this is a fun problem, okay? It allows me to also explain something about empirical formula. So empirical formula tends to be the simplified. Empirical formula shows the simple relationship between ions. Okay, so remember that simple or simplified relationship because that will be important in our formula here. Okay, so let me zoom in so we all can see. There are many different kinds of chlorine, so I'm going to section them out so we don't get overwhelmed. We're going to start with chlorine. Let me write this to the left. chlorine or chloride, sorry, here, chloride on top. So why don't we start with the corner chlorides? I'll say corner, okay? And I'm gonna number them so we don't forget. 1, 2, 3, 4, 5, 6, 7, 8. As I counted, we have 8 corner chlorides, right? And what fraction of those chlorides are in the unit cell, like we've learned so far?
1/8.
1/8, right? Doesn't change, 1/8. So from the corner pieces, we're getting 1 chloride ion. Okay, I'm done with that. Let me change the marker to a different color. How about black? Okay, so for the next group I'm writing, I'm gonna just count them out, right? 1, 2, 3, 4, 5, 6. Can you tell what pieces those are? They're not corner. Definitely not. They're not in the middle. What do you think?
Aren't they faces?
Yes, face pieces. Okay. The 6 I just counted, these are face pieces. What is the value of each face piece, or what fraction of each face piece inside the unit cell? This is that wall, right? Top, bottom, right, left. What fraction?
1/4.
That's the edge piece. This
Oh,
is, yeah, so the face is shared between 2 unit cells. So it's going to be 1/2. Remember the key I gave you guys earlier? You can go by that key. We're sticking with that key. Yeah, so phase is one atom shared between 2 unit cells, like side by side. And so I think of it like if you're living in an apartment complex and then you and your neighbor had, I don't know, managed to do something very, very not right. And you stuck something that went from one apartment to the other, but you kind of spaced it equally between the 2 apartments. That's kind of how I think of this face piece. It's spending half of it is in one room, the other half is in the next room, neighboring room. Okay, so 6 times 1/2, we end up with 3 whole chloride ions. Okay, am I done with my chloride ions? Looks like it. So because I don't want to write so much and then I'm going to just say this is the face piece. So I'll do the same thing again, this time with the purple ones. So you see the purple ones, right? I mentioned earlier the edge is from one corner to another. So this is one corner all the way to another. So this is on the edge. You see that? Edge. So can we count how many edge pieces we have here? 1, 2, 3, 4. The edges are kind of on the trim. I'm doing this hand motion like you can see my hands. On the trim between 2 corners. Okay. So between this corner and that corner is another edge. So that'll be 4, 5, 6, 7, 8, 9. Between these two here, 10. Oh, I forgot this one here, 11. And I forgot the one in the back here, 12. Oh, okay. So yeah, look between the corners and you see. So I found 12. 1, 2, 3, 4 on the bottom. These right here. These. Of course, when we're done with this, you can feel free to watch it for yourself so you can see. I got 12, right? So for sodium, I had, corner. I got 12 pieces. Does anybody remember what each corner is worth? So remember the corner is in the corner, right? And the corner is divided by 4. So you have sorry, let's just say corner. I am so sorry. I meant to say edge. I confused the edge. I just wrote up here edge, right? And I said corner. Sorry. The edge is what I should have written here. Edge is 12 times. So yeah, I should ask this correctly. What is the edge piece? Word. So go ahead and look at that table you have. The corner is worth 1/8. Yes, 1/4. So it's like this is 1 unit cell. You have the next one here to the left, one on top, and then the other one on the other top, right? So you have four stacked together. It's divided between four. And so this times this, it gives us 3, right? Man, when I'm doing this stuff, the math, left, right, all logic just goes out the door. Okay, I have one left. Oh, this is the middle piece. Can y'all see that? It's in the middle because it's between these two and those two. This is the middle piece, and that's the sodium by itself. So I'll call that the middle piece. And this middle piece is 1 times 1, so we end up with 1 sodium. So in the end, I have 4 total sodiums and 4 total chlorides, okay? We're being asked to figure out its empirical formula. So based on what we have here, you say Na sub 4, Cl sub 4. Metal first, write the number you got. Non-metal second, write the number you got. So remember I told you that empirical formula shows the simple whole number relationship between ions. I should say simple whole number. Anyway, simple. So we can't have the empirical formula like this. So you want to divide by 4 because it has to be simple. Now this is more complex. So we get NaCl. Okay. You want to divide it so you can have the smallest relationship possible because it's a simple meaning divide.
Can you go back over that a second again?
Which one? The simplifying part?
Yes. How'd you get to simplify?
Okay. Oh, so what I'm doing here, I'm dividing by the greatest common factor. Yeah, because I can't leave the empirical formula like this because empirical usually means like basic. Empirical molecular formula, I will leave it like this. Empirical formula, I have to divide by the greatest common factor, which is 4 between the two numbers to get a 1-to-1 relationship, NaCl. Okay, we're gonna work 2 more where we have to simplify, I think, in some cases. Okay, because remember it says simple, that means simplify if possible. So say for example I gotten 1 and 2, oops, not 1 and 2, but if I gotten 2 and 4, I'd have to simplify by dividing both by 2. And I'd have gotten NaCl2. Does that make sense? When they say simple whole number relationship, that means that make sure that the subscript are divided by the greatest common factor. Okay, did they ask for coordination number here? I see them reporting something, but okay, I see on the next slide. So based on this one here, what do you think our coordination number is? This is our central piece, right? What piece are in contact with this? If you were asked coordination number, what would you say? Can you tell what they are? Any takers?
6.
Yeah. Top, bottom, left, right, front, back. Yeah, that's what I see too. I see 6. I usually try to find the middlemost if there is such a thing. Yeah, the middle structure. Okay, this one here is gonna be fun. So we'll find the coordination number. We'll confirm it ourselves, okay? And then do the whole thing. Okay, let's go to this. Come on, zoom in. Work with me here. Okay, as I said, I like the corner pieces first. So 1, 2, 3, 4, 5, 6, 7, 8. So we got, I'll write it here. This is what? Zinc. Do I have anywhere else to write? I guess I could write it out here. Zinc 2 plus. For the corner pieces, I have 8 times 1/8 to give me 1 atom. Okay, and then let's see what else. Once I'm done with those, let me look for the color here. The other zincs. You zoom in, you see how it shows you the shadow here? There's a shadow. I hope you can see that. A shadow here, and all I'm seeing is half. Guess what half is? What is half? So I'm only seeing half inside the unit cell, right? That's. So I see 1, I see 2, I see 3, 5, 6. This is also half. If you look at that right there, right? It's about a half inside the unit cell. So what I see here is I see, oh, I forgot what this was. What's the thing called? He walked in here and I forgot. Face. Face pieces, right? I see 6 face pieces and each of them is worth 1/2. This is 3 atoms. Yeah, I was on a roll. Then my coworker here walked in. That's my husband. Just kidding with him. Okay, so I got all the zincs labeled. Let me go ahead and label the other ones. I want to erase it so that it's not distracting. Okay. So when I look at this here, right, I don't see any shadows on this picture. I'm not seeing any shadows at all. I see a shadow here. I see some shadowing here. I see 0 shadow here. So it makes me believe that these are inside. Do y'all see that? That these are in the middle, like a whole, not middle, but they're inside the unit cell. Like all 4 of these are inside because there's no shadowing in the picture. Okay. So for, oh, you know, I'm sorry, you guys, and y'all didn't say anything. I counted these right, but I labeled it wrong. The first one we're working on was the sulfide. The sulfide ions are bigger than the zinc ions because they actually gain electrons. What I'm working on right here, this is now the zinc ion. The zinc ions are smaller because they've lost electrons. Okay, so it looks right here that I have center pieces, and I have 4 of them. So 4 times 1, I end up with 4 atoms or ions. Okay, so we have 4 total here, and we have 4 here. So as usual, you write Zn 4 S 4. Don't write the ions, just write the elements. Divide by 4, divide by 4. You end up with Zn S. And that is the empirical formula. You're dividing by the greatest common factor to get the simplest relationship, the simplest ratio, 1-to-1, right? Z and S. The coordination number, they said it was 4. Let's see if we can see that. If Zn is your focal point, you can see how these 4 are surrounding the Zn. So when they're packed together like they're supposed to be in the solid, those 4 surround the Zn ion. Okay? Okay, so we have 1 more to go, wherever the picture is. Oh, there it is. Okay, again with this one here, we're going to be doing empirical formula, and then we'll be doing coordination number. Okay, then they have 2 different ones here. So we'll see. Once again, we'll go over the corner pieces. Let me make sure I'm labeled this right. Yeah, I can tell I'm already getting fatigued after this being the second class, but hanging in there for a few more slides. Okay, so right here I have calcium ion. We're looking at that first. Let's look at the corner pieces, right? 1, 2, 3, 4, 5, 6, 7, 8. Let's get those out of the way. Corner. 8 times 1/8 equal 1 atom. Okay? Now, these are the ones. Once again, I kind of look in here, and if you can see this carefully, can you see the little shadow? There's also a design. I wonder what that is. But anyway, the shadow, right? It's kind of right here separating the atom in 2. So it's like half inside the unit cell, the other half outside, making this a face piece, right? Face. So I'll call that 1, 2, 3, 4, 5, 6. 6 times. Each face piece is 1/2, right? 3 atoms or 3 ions. Okay, let me see. I did all the teal / gray / slate color, whatever that color is, the grayish, whatever. Then now we're doing the yellows. The yellows are F-. Okay, now I'm looking at these. I'm not seeing any fancy shadows. There is a reflection, but it's not really a shadow. I'm not seeing any shadow on these. So I think they're all in the middle. Plus, you see how the bonds kind of converge on them? So I'm pretty confident they're in the middle. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Right. They're within the cubic cell not outside, right? They're not on any of the walls or any of that stuff. So we have, I just call them center, but they're within it, right? I saw 8 times 1, so we end up with 8. Atoms, ions, whatever. Atoms, ions. Okay, now that we have that, we're going to be doing our math to say Ca, when you add these two, you get 4, right? Ca sub 4, F sub 8. But this is an empirical formula, so you have to do the simplest. Divide by 4, because the greatest common factor between these two is 4. Divide by 4, divide by 4, you get CaF2, right? The empirical formula. Empirical. We have one more. We have to do the coordination number. Oh, that will be fun. The coordination number for fluorine, which should be confirmed, right? Okay, what do y'all think it is for fluorine? I have my speculation. What do y'all think the coordination number is? Coordination number for fluorine. You tell me what you see and I'll tell you what I see. It does look a little complex, right? But you want to look at many of the fluorine ions and see what are you seeing connecting with the central one that you're focusing on. Anybody got a hypothesis, an answer, suggestion, whatever? Am I alone? Did you all go and get lunch?
I got 8.
You got 8
Yeah.
from
Or
fluorine? Where's the other?
oh, okay. I see what you did.
Yeah, I'm just trying to use. Listen, when words comes to words, I start with the bonds and then I move on and see there's something else I'm missing. Yeah, when I look at those, I see 4. Now, could it be more? Probably. I don't know. What did they say? Oh, they put it right here. Yeah, they say 4 for fluorine, so I see 4 too. Now, calcium, they say 8. I don't know. Let's see. Let's see. Just because they say doesn't mean I necessarily see it. Okay. Let's see if we can find 8 for calcium. This calcium ion here, I only see 4. This other one, I only see 4. This, I also only see 4. All the calciums here, I see 4 or less, right? So that means we're missing. If they had given us one more cubic cell right here, and then they showed us the remaining 4 here, I could have seen 8. Okay, just because they wrote it here doesn't mean you can see it, because I'm looking at this and I'm not seeing 8. We need more unit cells to tell that, right? But we just agree with what they say because it does, yeah. So sometimes you can have different coordination numbers based on what they give you. So they say there's 8 here. I honestly, I only see 4. But yeah, so with this information here, you should be able to do your first 3 labs, right? And we made it. Only 8 minutes over. Any questions? So if you missed, if you were only here Tuesday and Thursday, there was one video that I shot with Jacob yesterday, and that covers the content in between. So feel free to watch that. It is already posted on the in the collaborate folder. Okay. Other than that, guys, this is all I have for today. I feel like there's a meal somewhere with my name on it. So any questions? So go ahead and work on your lab, and if you do have any questions, feel free to send me email.
Okay. Thank you.
Okay, other than that, have a nice weekend.
You too.
Bye.
Bye.
Bye, Rocio. I don't know who else was logged in, but oh, Leanne, Samuel. Bye.